Hi there, this is Mr. Sand again, and this is going to be conserving energy. Now, lots of really good explanations are out there that go into more detail than I'm going to go in today, but I'm going to give you the basics. I think we just need to touch upon this. This is a very deep idea that runs through physics, and that is energy. Energy cannot be created nor destroyed. So, uh, So, you can't create energy, you can't destroy energy, you can just convert energy. So remember what energy was? Energy is the ability of something to do, to change something else, either itself or something else. So you cannot create energy, you cannot destroy energy, you can just change energy. Um, that's the main idea of conserving energy. Today we're going to talk about changing one type of energy into another type of energy. We've been already talking about the kinetic energy. So now let's go towards the other type, the other weird type. And that type is called potential energy, and specifically gravitational potential energy. So we already said that work equals force times displacement. So if you have something that's moving, let's say it's a apple, it's moving along sideways like this, that force it's pushing it, if it's moving along sideways, that force it's pushing it on that along that distance, so it's going a distance s, that is work. Work times force, work equals force times distance. Now, that apple's pushed alongside here, but now let's just tip it on its side and give these things different names. So if we tip it on its side, just rotate this entire thing 90 degrees. We've got an apple, sort of. It's a yellow apple, and then it's force, and its displacement is right here. So this is S, and this force going downwards like this. And now I'm just going to do this. I'm just going to put a little grass down there. Okay, so now this has turned into a completely different, a different kind of look. No longer is it going sideways with the force going that way. Now it's going straight down, and grass is at the bottom. And there's a displacement going from here to there. Now, in a gravitational field on Earth, this force is gravitational force. So I'll just put a little g there. And it's in line with the object's motion. It should go straight down. So the force, if this object is going straight down, that force in line with that is just Fg. And remember what Fg equals. The force equals the mass times the acceleration due to gravity, which I'll just put as g. And this S right here, we can call that S short displacement, but we normally call this the distance from wherever it is to the ground. We call that the height. So I'm just going to abbreviate that with H. Okay? So work equals force times displacement. Well, in this case, the force is mg and the displacement's height. So in this case, work equals mg times height, mgh. This right here is what we call gravitational potential energy. Gravitational potential energy. We call it gravitational potential energy because if you have an object that's suspended from the ground at a certain height, gravity it can do work on that object. As soon as you let it go, it will do that work. It's as if you've got kind of like work stored up, ready to be released whenever you let go of this apple. Okay? So this gravitational potential energy, we often abbreviate that as PE. So PE just equals, I'll just write it down over here, PE, potential energy, equals mgh. All right? Okay, that Should be fairly straightforward right there. Now what I'm going to do is I'm going to say, great. Well, this object, as soon as it starts moving then, if you let it go, it will then start to get kinetic energy. Weird. And at the very bottom, there'll be no gravitational potential energy because there'll be no height, right? And all of that energy will be, it is potential at the top here. It'll be converted into real live energy, kinetic energy. It'll be energy of motion. So I'd like to write some sort of an equation that would kind of like describe that scenario. At the very top here, it's got all potential energy, and at the very bottom, it's got all kinetic energy. So I could say that the total energy of this little apple right here is at any point along this drop, it is all of the potential energy plus all of the kinetic energy. So the total energy of this little apple right here, actually there's also chemical energy stored up in it as well that we'll use to power our muscles and all sorts of things. But we'll just call this mechanical energy. Maybe that's a better way to say that, but that's just total energy, total mechanical energy. That's a better way to describe this. Mechanical energy. Yeah, that's a better way to describe it. And at the top there, it's got the total, that big E, and then it slowly, as you go down, it has more kinetic energy. It gets more and more of that, and less of this. So we can write actually another equation. This is even better to describe the scenario of this apple falling along here. We can say that the initial kinetic energy plus the initial potential energy will always equal the final kinetic energy plus the final potential energy. Okay? The very top here, this, the KEI, the kinetic energy, the initial kinetic energy, that is 0. So that would just drop off. So it would be potential energy. And now, if we can choose any point along here. We can choose that point, that point, that point, any point along here. And we can say, okay, at that point, we've got a certain amount of kinetic energy, and we've got a certain amount of potential energy. But we know for sure at the very bottom, right as it hits the ground, there is no potential energy. So then that term will turn into 0. So we could say that the initial potential energy will equal, if we want to, this will equal that. And that's pretty cool as well. So all of these equations, this, so I'll star them. This one, I'll put little boxes around all of them. This one, and this one. These are all important for today's problems. Let's look at a problem. Warm-up problem number 1. I'm going to get a new